and even some of these are around and doing well, so it's great to be back. This admittedly somewhat hyperbolic title, the world's youngest, is sort of my Australia version of this talk, which I've given in different versions, in other places. In Australia, typically as a geologist, you start with the world's oldest, and you have a lot of world record-breaking old rocks here. And it's especially in Western Australia, where I'm now. So this is just to maybe take a slightly different perspective and look at young active systems, which may actually help you to understand the older systems, because in these young systems, you can look at processes in the making and hopefully get a better understanding. I'm not saying that we will understand carbonatite magmatism by only studying Laacher See, but there may be some lessons to be learned. And the results that I'm going to show you is always a little slow, but I'm hoping.
Oh, we just started the recording. You might need to hit OK.
Okay, maybe that's yeah, right. That's probably what it's waiting for. Let's try that again. Let me also to get the pointer so that this works. It's still not moving forward. Okay, there we go. There were several collaborators involved in this project at different stages, and I just wanted to highlight some of the students that were involved. Tracy Howe, she actually worked on the project when I was still at UCLA. Fabian Schmitt in the middle, he was actually a master's student who just finished 2 years ago. And Florian Wetzel was also at the time at UCLA involved in some of the projects that the results I'm going to show. I know there's a lot of people here that I assume think every morning when they get up about carbonatites. We already had some really great discussions, but maybe for the rest of you, I just want to remind you, why do we even care about carbonatites? Well, carbonatites are an important source for many critical metals, especially the rare earth minerals. And you can see that, if you look at your cell phone or your electric toothbrush at home, all these consumer goods, plus, for example, wind turbines contain permanent magnets, which again contain rare earth elements. And as we are transitioning to a zero-emission economy, there will be more demand for these devices. And what we currently have is not enough to, even if we were able to recycle the entire stockpile of rare earth that is currently in circulation, we will not have enough. So we have to get more out of the ground to feed into this cycle. And where do we get them? Where do we find these rare earth elements? Technically, these are the lanthanides, but then often also the geochemically similar elements, scandium and yttrium, are included into this group of elements. And we get them from ores, and the main primary ore, and it's not only from terms of mass, but also from the quality of the ore, because it's certain rare earths that are particularly useful for these industrial applications. They come from this rare type of rock called carbonatite. So in order to enhance our ability to transition to a net zero clean energy economy, we have to find more of these rare earth elements in carbonatites. And if we look at the current situation, we're pretty much, a little bit beyond this 2020 time mark here. You can see there's actually all the major sources of rare earths are carbonatites. There are 3 major sort of like world-class deposits in the world. One is in China, Bayanovo, and that is pretty much 50% or so of the world's production currently. There is the Mountain Pass carbonatite at the border between California and Nevada. And then in Western Australia, we have the Mount Weld carbonatite. And the prediction is, in order to satisfy all the needs, we have to increase this production by 2050, essentially to at least 450 kilotons per year, which is, a 50% increase that is required. So there's clearly some need to study and better understand carbonatites and how they are related to these rare earth deposits. So what are carbonatites? By definition, it's a magmatic rock that just contains more than 50% of carbonate minerals. And I think, yeah, the video is going in the background. They're sort of like one really active currently, actually, I don't know currently in the terms of if it's right now, but in very recent history, erupting carbonatite volcano in Tanzania. That's this Oldonyo Lengai. You see sort of this video in the background. This is the summit region. And these are sodic carbonatites. They are extremely fluid magmas that erupt at low temperature. And you can sort of see this swing out. It looks like muddy water, but it's actually, melt. It's about 600 degrees or so, the temperature at the time of eruption. That's sort of an oddball. We only have one volcano of this type. And actually, most carbonatites that we find in the geologic record are plutonic rocks, and they are essentially exclusively calcium mineral containing carbonatites, mostly calcite, but there are also some dolomitic carbonatites. And there are different genetic models how you can actually form these carbonatitic melts. And I'm not going to talk too much about where they actually form in the mantle. I'm more interested, and actually some of you actually mirror this sort of interest, what happens to these carbonatites when they ascend and when they differentiate in the crust or form in the crust. How do they influence or interact with crustal rocks, and how do they form ore deposits? But the idea is in general that they form in the mantle. We know that, and actually I'm going to show a slide. We know this in part because of studying Laacher See in the very early days. If you look at compilations of review papers, and again, some of you have been authoring some of these really excellent review papers. I don't have those on here. I just copied this from other papers. You sort of, how do people think carbonatites look like structurally? So there's always on the surface, a volcanic edifice that is associated with this, often with an explosive volcanic structure, so a diatreme, for example. And then we have the subsurface underneath these volcanoes. And typically what we see are these components that are listed here. So we have carbonatite intrusions, and then we have usually associated with this, in most cases, also some silicic rocks, intrusive rocks. Again, mantle-derived alkaline mafic rocks, often as cumulates, and how they form in exact way is still a matter of debate. And then we have a hydrothermal aureole that's surrounding it. And you can look at these sort of like stamp-shaped sketches, that are shown here. Actually, you should use the mouse a little bit more often here. They all emphasize different aspects of these components, but we pretty much always have sort of these essential elements, intrusive carbonatite, and it's associated with silicate rocks and hydrothermal alteration interaction with the country rock, especially by alkaline fluids. The term that is used is phenite. These are then phenitic alteration halos around these intrusions. These are the essential components. And this is also where we find the rare earths. And there are different types of deposits that are associated with. They also reflect different mineralogies. There are sort of primary magmatic deposits in the intrusive stage. For example, the niobium mineral that also contains a lot of rare earths, pyrochlore, that is actually found, in these magmatic carbonatites. But then we also have a hydrothermal stage in the phenites. These could be different other types of minerals, sometimes carbonates, sometimes fluorides or fluorocarbonates. And the third type is, okay, what happens when a carbonatite weathers? We can actually also get supergene deposits. And this is what makes Mount Weld in Western Australia such a great deposit. It's essentially a laterite horizon developed on a carbonatite intrusion. So what are the key questions? And again, I compiled this from some of the recent review papers, and I don't want to read them all, but one essential question, is this first one, what is actually this relationship between the silicate rocks that we find and the carbonatitic rocks? And then we have a whole lot of other questions regarding the origin and so on that are also of interest. But I sort of want to mainly point my finger on the first point here. What is the relationship between silicate and carbonatite rocks? And why is this important? One important aspect, and that's also if you are going to do exploration, you want to look for a geological province to potentially find hidden carbonatites, and it's good to know how large these provinces are, and especially in which geological context they form. In other words, how old they are. If we now look at dating carbonatites, it turns out these old carbonatites are actually not that easy to date. This is sort of the world's largest rare earth deposits by an ovo, and I took this figure of a recent study, 2021, and they already nicely compiled all the ages, uranium, lead, zircon ages that exist for this carbonatite. Okay, pick your age. How old is by an ovo? It's not easy because, as we know, often zircon, can contain inherited domains, inherited country rock, but also often these carbonatites are typically highly differentiated magma, so there's high abundances of incompatible elements, accessory, that then get incorporated in these accessory phases, such as uranium and zircon, which of course makes the zircon vulnerable to metamictization and lead loss, young ages. So currently the best estimate is based on a recent study that looked at zircons. You can sort of see how they look like, Zhang et al. 2017, from a carbonatite sill. And if they average, their in situ analyses for uranium lead, they get an age of 1300 plus minus 12 million years. This may not be the most precise age that you can get from zircon. Maybe with TIMS, you can try to beat analytical precision down to if you're really lucky, 0.1%. So that would be about plus minus a million year. But a million year is still a large time interval, especially if you want to answer the genetic relationships between different rock types, these silicate and these carbonatite rocks. Bayan ovo is not the only case where zircon is sort of like a problematic mineral to study carbonatites. This is sort of the second largest deposit in the world. This is Mountain Pass. And again, this is a compilation of data. Kate Watts is the first author from the USGS. And on the right side, you see a Concordia diagram. So, and the first thing, of course, is that a lot of the data are not on Concordia, they're discordant. And again, we have lead loss that makes things complicated. That's why on the left-hand diagram, the authors only show the 7-6 ages. And pretty much sort of, this would be corresponding to this intercept. Sorry. And that would be in the neighborhood of this age here. So this is what they interpret as the carbonatite age. But then again, there are silicate intrusions associated with Mountain Pass. They call them shonkinite or syenites, intrusive alkaline rocks. And the best ages they get from them are sort of, in the 1415 range, which makes this like a 40 to 50 million year time difference, but then also you have huge uncertainties. So is there really a genetic relationship between these silicates and these carbonatites? I don't think you can really decide for these old systems. And the last problem that I want to mention is actually, I keep talking about zircon and a carbonatite. Carbonatite have very low silica abundances, which also means that typically their silica activity is low, and therefore they actually don't form zircon. They would form zirconium oxide bdelliite. So if you date a zircon from a carbonatite, you have to ask yourself, well, where does it actually come from? Why is there even zircon? So this is now where this volcano in Germany comes in, Laacher See, and it is officially listed in the catalog of carbonatites, worldwide. We're right here. Mount Weld is down here, and it's been actually studied for a long time. And I mentioned some of these early questions regarding where do carbonatite magmas come from were addressed using samples from Laacher See. So originally, it was thought that carbonatites are just molten carbonate rock. Okay, so they would be of a crustal origin. with the advent of isotopic techniques, oxygen isotopes, and Hugh Taylor is the first author on this study, they looked at these oxygen isotope and carbon isotopes from Laacher See and Aulo in Sweden, carbonatite, and they determined that they have a mantle oxygen isotopic composition, and hence they cannot be just molten crustal limestone. So that was a groundbreaking study that was already involved in where Laacher See was already involved in understanding carbonatite genesis. And I have a sketch here, again, sort of this schematic how people portray carbonatite intrusion underneath volcanoes with these constitutive elements that I mentioned, volcanic overburden, a diatreme structure, alteration halo, and then this association between carbonatites and possibly different types of silicate rocks, different types of differentiation, evolved or mafic, alkaline, intrusive rocks. And from a completely different study on Laacher See, this is how people think Laacher See looks like at depth. And of course, there's always geofantasy in these sketches, but there are some good reasons where this sketch comes from. It's informed by observations on the surface, and I will talk about this in the next couple of slides a little bit more. But I think you can sort of see the similarities. There's essentially the same types of structures, maybe not the same volumes that are involved. So at Laacher See, we think that carbonatite is actually a very, very small part of the entire system. But then again, it's a system in the making. There's no indication that the magmatism in the Eifel and in Laacher See has really abated and stopped. So that's why I think it's a good natural laboratory to study some of these processes. And in the next couple of slides, I just would like to show you a little bit more detail about, okay, where is this volcano and what's its geologic context and what do we know about this magma system? So first of all, it occurs in an interplate mafic volcanic field, not unlike the newer volcanic field in Victoria and South Australia. I've sort of even outlined here on the same scale. This is this tertiary, quaternary, newer volcanic province, and that is in fact even bigger than the volcanic fields in Germany. There's the so-called Central European volcanic province, which includes the Eifel, where Laacher See is located, but also some other older fields. Some of you may have heard about Kaiserstuhl, which is also a carbonatite, but it's an older carbonatite. It's about 14 million years old here in the Rhinegraben. So these are part of this interplate mafic province. If we actually look at, even zooming into the volcanoes in the Eifel, you see that there are lots of volcanoes. There are about 240 scoria cones and Mars in this red field, which is the West Eifel. And Laacher See belongs to the East Eifel province, which has fewer volcanoes, about 80 centers, but some of these volcanoes are relatively big. And there are 3 phonolithic centers, one of which is Laacher See, and they sort of erupted orders of magnitude more magma. We talk about magma volumes of 10 to 15 cubic kilometers in a single eruption. If you would count all these scoria cones together, you probably don't even get a cubic kilometer. So by volume, the actually smaller field with Laacher See is the bigger player. It's the more important one. I mentioned that magmatic activity in the Eifel is still ongoing. What's the cause of this magmatic activity? We know that there is a hot mantle anomaly actually centered underneath the Eifel. So the Eifel, where Laacher See is located, is this black triangle, and the surrounding mantle at a depth in the asthenosphere is about 150 degrees centigrade hotter than the surrounding mantle. So it sounds like the interpretation is there's a small plume or plume finger that is driving this type of magmatism. It also is the center of uplift in entire Central Europe. If you look at the vertical land movement, this red area here is sort of the hotspots, and we have about 0.4 millimeters per year uplift. that is centered underneath this volcanic area. There are earthquakes. Some of them are tectonic earthquakes. So you see again, like this is a map of the East Eifel. The red triangle is Laacher See volcano. You can see these green dots. This is a fault that is parallel to the bounding faults of the Rheingraben. These are tectonic earthquakes. But then there are also deep low frequency earthquakes that are indicated with the stars. They are sort of in a lineament that extends to where Laacher See is. And geophysicists interpret these low frequency earthquakes as movement of fluids. Could be CO2, could be water, could be melt. That's not decided, but these earthquakes definitely transgress, excuse me, the entire crust, from the Moho up to 10 kilometers. Okay, and we have actually, CO2 bubbling out of Laacher See, even today. So there is outgassing. So CO2 certainly plays an important role in that entire magma system. So I showed you this sketch integrated into another figure before, but this is sort of like honing in on what we think the magma system looks like at depth. And for example, the depth is constrained by melt inclusion studies, volatiles and melt inclusions, and by experimental petrology. So we pretty much have a good idea where the crystals that erupted in that Laacher See eruption formed, and that's about 5 to 10 kilometers depth. The eruption itself, you can go in the field, and when you look at the stratigraphy in detail, you can see that's a zoned eruption. It starts with very evolved phonolites. They have about 2,000 ppm zirconium, very, very low abundances, for example, in strontium, though they are extremely differentiated. But as we go up section, we get to this middle Laacher See and the lower Laacher See tephra, all erupted in sequence, and we're not talking about hiatuses or breaks in the eruption here. It's a continuous sequence to more, it's still all phonolite, but this is more primitive, less differentiated. And if you do thermometry and volatile abundances, you can basically invert this stratigraphic sequence in the field to a reconstructed magma chamber, which has cold, volatile, crystal poor magma, very evolved at the top. And then it sort of gets into this more crystal rich, harder, and volatile, poorer, deeper part of the magma system. What is also interesting, and that's sort of indicated by this margin of the chamber and also this apophysis on the top, there are often plutonic ejecta that came out with the eruption. And that's essentially the focal point of my talk, are those plutonic ejecta. And some of these are carbonatites. So they must come from the shallow part of the magma system, because we know that the magma was stored at 5 to 10 kilometers depth when it erupted. And it could have only brought things up, from that level or higher. So this is most likely, and again, a little bit of fantasy. We don't know if it's here on the top or maybe it's on the side or so, but at least it's part of this shallow upper crustal magma system where we find these carbonatite rocks. And just to give you an impression, how do they look like? There are different types. Some of them are more dike-like, where we have here all these blady minerals, kind of brownish pink in color. That's all calcite, so they're silicic carbonates associated with silicate rocks, which is mostly vanadine. And the mafic phases is some amphibole, but also a lot of magnetite. And this is, for example, a bleb of carbonatite rock in a silicate rock. And that was based on this hand specimen size sample. We interpreted this as evidence for liquid immiscibility, because it has these undulose margins that sit against this silicic syenitic host rock here, but with sharp boundaries. And you can see how this is sort of elongated. This is not uncontested. Some people say, well, this is shearing, this is a solid rock that was sheared, but I find that hard to believe, because we see no evidence of shearing in the surrounding host rock. There's another recent study that came out, Bernd et al. From the Münster group. They looked at melt inclusions in a mineral that I forgot to mention. It's a feldspathoid, hauene, that occurs in these Laacher See pumices. And these melt inclusions, if you look closely, when they looked at them closely in the study, they basically found that they consist of these rounded carbonatitic, Ca calcium carbonate rich blebs. And then there is an outer part of this melt inclusion, which is phonolytic in composition. So that's a silicate composition. And you can see there's a little bit of, this calcitic droplets. They also exist in this silicate melt. And again, this would be then texturally interpreted as evidence for liquid immiscibility. And that is hosted here in hauene. There is some debate about how well they did these measurements and what the exact compositions are, but I think at least texturally, there's again strong evidence that that liquid immiscibility is an important process in the evolution of the system. So I would like to now talk more about timescales. I mentioned we have this problem in how do we link carbonatitic and silicate rocks in older systems. So if we look at a very young system, we can actually use a dating tool that is not often used in Australia because there are no young rocks, and that is disequilibrium dating. So what is mostly done in uranium dating is you have uranium, and I'm just using here uranium-238 as an example, as the start of a decay chain, and the final product that is typically then measured to determine the age is lead, in this case 2,6 lead. But this decay chain has short-lived intermediate isotopes, among which the most important one for our purpose is 230 thorium. It has a half-life of about 75,000 years. In old rocks, we have radioactive equilibrium in the system. So essentially for every decay of a uranium-238, you will also register a decay of 230 thorium. This radioactive equilibrium can be disturbed, for example, by crystallization. So if we have a bunch of minerals forming from a melt that have different partition coefficients for uranium and thorium, they will not discriminate between the thorium isotopes. Their mass difference is minuscule, but they will end up with different uranium-thorium ratios. And that is sort of, time zero with regard to our disequilibrium clock. Then, as time progresses, after one half-life, that deficit that we initially had in 230 thorium will become smaller because we have an ingrowth in this intermediate isotope 230, which means that our points move upward. If we had points on this other side of the one-to-one line, they would actually move downward and approach again, this one-to-one line, which represents equilibrium. So after 2 half-lives, you can see 3 half-lives, 4 half-lives. Eventually, we end up analytically indistinguishable from the one-to-one line, and that essentially is after about 5 half-lives. And given that it's 75,000 years, we talk about 300 to 400,000 years, where we then cannot use this method anymore. But then that's where uranium lead again comes in. So we sort of are looking, and I will show you a bunch of these isochron diagrams. So essentially in this little sketch, you can sort of see it's a backwards rotating clock. So 0 is horizontal, and then your pointer essentially moves up until you reach the one-to-one line. And that's sort of the time that we measure. So every time a zircon is not on the one-to-one line, we know it has to be young. And if we do these are the samples from Laacher See. One particular zircon, multiple spots. It's unfortunately not the one that I have here in the figure, but it's basically the same story. If you do multiple spots, the data are not on the equiline, which is this red line here. This is the one-to-one line. But they fall off the equiline, and you can do a linear fit. And that regression gives you a slope, and that slope corresponds to age. And in that case, it's about 36,000 years. So that would be that age of that zircon. You may notice that the MSWD, this measure for the excess scalar, is slightly elevated. And that's because that zircon may actually have a finite growth time, or it may have experienced, as we see here in the CL image, some dissolution reprecipitation, which may have reset the thorium clock. So there's a lot of complexity, a lot of interesting information that we even haven't really fully addressed yet. So what do we get when we look at these carbonatites? So this is now a compilation of zircon ages from hand specimen-sized carbonatites from the Laacher See that erupted as individual ejecta clasts. Every point is a zircon analysis, and so we look at different zircons in these samples, and you can immediately see they're not on the aquiline, and we get different ages, and I don't want to go through all these diagrams, but we get pretty much ages that range from the time of eruption, which I think I forgot to mention that, sorry, 13,000 years it erupted. It's well dated by C14 dating. So we pretty much have zircon ages that are analytically indistinguishable with the eruption age. So zircon must have crystallized just before to about, again, for these individual hand samples, about 33,000 years. This is sort of the oldest isochron that we have. So that means about 20,000 years before the eruption, these carbonatites or these carbonatite-bearing rocks were forming zircon. There was already zircon crystallizing. So that's, of course, an important aspect with regard to magma residence times and potential early warnings. I also want to show you another use of uranium-series isotopes in that diagram. And that actually is not zircon dates, but this is now whole rock data. So we can take these samples and crush them and analyze them in bulk. And we get a uranium-thorium and a thorium isotope ratio. And since we know the decay constant, we can actually back calculate how this thorium isotopic ratio, which is not fractionated by magmatic processes, it's only changed by age, has evolved through time. Okay, so every point here is one of these xenoliths. Some of them plot off the scale here, so they would be somewhere up here where these arrows are pointing. But if we back calculate them based on the uranium abundance, how the thorium isotope composition would change, we can follow these lines. And then we can look at, do these lines sort of intersect? And especially, how do they relate to the silicate line? So the black symbols are all the carbonatites. This is now a silicate. So this is the pumice that erupted in the Laacher See eruption. And you can see that in all these cases, for the carbonatites, the ratios go down when you go back in time. That's because they are on the right side of the aquiline. The silicate part is on the left side of the aquiline, and actually, when you go back in time, that ratio increases slightly. And that's the eruption age. So these lines are not allowed to intersect after the eruption. Now, that would be bad if they did, then we would have a problem. Fortunately, they don't. And they intersect in an interval that is shown here. So this is basically the range in age over which the carbonatites, which are these thin lines, and the silicates had the same thorium isotopic composition, okay? And that's actually an age that is reasonable and matches well with the range of the zircon xenolith ages that we have, except for this one older sample that I included here. We don't have a bulk analysis for that one because it was a very small sample. But for all the other ones, actually the zircon crystallization and this last equilibration age between carbonatite and silicate closely overlaps. So you can use thorium isotopes pretty much in the same way as you think about strontium isotopes or neodymium isotopes. They are not fractionated by magmatic processes. And if you have the same, let's say, neodymium isotopic composition, that basically means these are really the same isotopic compositions. And to some extent, that's a good indication that they're cogenetic. So we have the same time, and based on this thorium isotopic composition, we have the same composition. So I think that is a strong argument that silicate and carbonatite melts are closely related. And the interpretation that we favor is that the carbonatites evolved by immiscibility, segregation of a carbonatite melt from this highly evolved phonolytic melt, based on this isotopic similarity, the similar age, and the textual evidence for liquid immiscibility. Okay, I now want to shift gears a little bit and just show you some more recent results. It's sort of like a COVID project where we were stranded. We couldn't do fieldwork anywhere except for inland. And so I had a master's student at the time. This is here, Fabian Schmitt. We're not related. It's a different Schmitt, but the same last name. And we thought that, let's do something in the Eifel. And the question behind our project was, all the data that I've shown you are for these individual plutonic ejecta. They're pretty much randomly sampled by the volcano at depth. We don't really know where they come from, except crudely, probably from that shallow part of the magma system, but we have no idea about their geometry, and we don't really know how representative they are. We could try to sample more, but we thought we want to do a different approach, and I don't think this has ever done, a detrital study of a young volcano. So we did a hydrologic analysis of the Laacher See, and you can sort of see in pink, these are the surrounding pyroclastic deposits. And I mentioned that there are two other centers, two other evolved photolithic centers. You don't have to remember the names, but here they are. This would be the Wehr Center, with the green deposits, and the blue center, the Rieden Center. This is between 100,000 and 200,000 years old, and this is about 400,000 years old, based on Argon ages. And when we did this drainage analysis, we thought that it's actually a very simple system. There are only two rivers that drain pretty much that entire volcanic area. So if we strategically sample sediments from the endpoint of the rivers, and we took, for good measure, some points a little bit upstream, we thought we would capture the entire volcanic systems, including these two precursor eruptions, and we would get a better idea about, looking at zircon, when did this magma system actually initiate? And so we took these gold washing pans and rubber boots and went in on a cold March day in this not too warm river, and started panning for zircon. And sure enough, there's plenty of zircon. And let me show you the ages. So not unsurprisingly, we got a lot of old ages. There's one analysis here, which is about 3.2 billion, so pretty old for Germany. But most of them are, in this range, Paleozoic ages, and that's essentially the crustal age. There are Devonian shales makes up the country rock in the region. So these are all detrital zircons. There was a little surprise. We didn't really expect that. Some Paleogene volcanic zircons. So the Eifel volcanism, what I talk about is all the quaternary phase, but we know that there was also an earlier phase between about 40 and 20 million years. And sure enough, we found a lot of these 40 million old zircons, which we didn't know existed. And they are related to this older phase of volcanism in a very similar setting, very similar compositions. So also alkaline rocks. But then, so if you look at this pie diagram, so what I just showed you was this basement, which is about a quarter of the population. Then we have these Paleogene volcanics, 10%. But the vast majority of the zircons in the modern river sediment is actually from Laacher See. And we know this because they are younger than 100,000 years. If you look at these isochron diagrams, again, here's the initial sort of what you would expect if it was zero. The green symbols are all what we interpret as derived from these quaternary rocks because they're in disequilibrium. And these open symbols, I don't know how I did that. I kind of have to. That's not what I wanted. Okay, comes back. These open symbols are essentially all the grains in equilibrium, for which I showed you the uranium-lead age. And so if we look at that, we again have ages around 15,000. We have ages around 30,000. If you look at these peaks. But interestingly, for these three samples, which are dominated by Laacher See-derived detrital grains, we now actually get older zircon. We can push back the onset of zircon crystallization to about 60,000 years. So we now have about 50,000 years of magma residence where zircon crystallized underneath this volcano, which is only 13,000 years old. So again, the longevity of the magma system is very important, very interesting for this volcano. The not unexpected result is, or the different result is for this northern drainage basin, which is called Brobach, where we found a lot of zircon from these earlier centers. We did not find any zircons that were around 400,000 years, so nothing from this Reading complex, but a lot of zircons that's essentially related to the precursor to Laacher See, this Bear volcano, and then actually only very few Laacher See zircons, which is kind of surprising. So we only found 2 of them. So that essentially, it doesn't really change the story, but it makes the whole lifetime of the system even longer than we thought based on the individual hand specimens. So now coming back to, these large carbonatitic systems, and we want to know, when did they form and how are silicate and carbonatite rocks related? I'm just putting up this slide again for Baia Novo, where we sort of have this best estimate for zircon ages from a sill with uncertainties of 12 million years. If we now take, on scale, our age resolution, which is this white bar here, this is now what we can resolve as pre-eruptive zircon crystallization in the Laacher See system that happened over 50,000 years. You are not able to distinguish or discern processes that happen over these 50,000 years in an old system. Your age resolution is just not there. So that's why I think, it is important to look at these young systems, because you can learn lessons about how different rock types are related, where you don't really have a chance to do this with confidence, at least with regard to the geochronology on older systems. Okay, so I hope I could introduce and interest you in this volcano in Germany, Laacher See, a highly evolved alkaline system. We now know that this evolved magma that's capable of crystallizing zircon, and it's not necessarily the carbonatite itself. I actually think the zircon crystallizes in the silicate part of the magma system, and then we have mixing between carbonatitic and immiscible silicate melts at a later stage. That started about 50,000 years prior to eruption. And we know that the carbonatites and the silicates, they are coeval at this high resolution, and they share the same thorium isotopic composition, which means they were in isotopic equilibrium within the time scale that we know the system was active. So I think based on these results and also the other evidence based on textural and melt inclusion, I think this shallow egg solution within top of a highly evolved CO2-rich phonolite can generate carbonatites. And that basically means that carbonatite magmatism can happen in the upper crust. So the carbonatites, even though the whole magma system is fed by mantle processes, probably the vehicle that brings the magma up are these mafic melts. The precursor melts were these phonolites, basanites, and they differentiate in the upper crust. And if you take fractional crystallization to an extreme level, you end up with these shallow carbonatites. Okay, thank you very much for your attention, and I'm happy to take any questions. Oh, do we have questions? Yeah, Michael.
As you said in the beginning, zircons shouldn't exist in carbonatites. Did you find anything else?
Yes.
Did you find any badlites?
Yes, there is bedelliite, and I would like to follow up on that and look at the bedelliite. The bedelliite is actually also in the river sands. We have it in some hand specimens, but we also find it as detrital grains, but we have not looked at it closely.
Something that would be interesting is that you dated the time that I would say that one that separated from the silicate.
Yeah.
Now, at that time they were included. So that's a time where they should not make any zircon, make other things, unless there's something with effectivity that we don't understand, which is what we talked about earlier.
Yeah.
But it would be very interesting to see what are the ages that you're getting from the body ice.
Yeah.
Because if they're younger, then it shows you some kind of coupling of the silicate.
Very good point, and that's exactly sort of what I would like to do in the future. The only problem with that is, of course, what if the process repeated itself? You know, you had multiple phases of silicate-carbonatite evolution at different times within this time window. So you're right. You know, you would maybe expect the Buddella to be younger, but that could have also happened, you know, at an earlier stage. But then I think when you look at enough samples, maybe you'll get some statistics. You know, maybe everything is systematically shifted, but that's hopeful thinking. Usually nature never works like that. Maybe?
Interesting talk, Axel. I enjoyed it.
Thanks.
Beautiful slides. I have a question about, so you showed the plot of all of those ages, and you said pick your age. Could you show that again?
Oh, yeah, okay.
It's
Yeah.
three slides.
Yeah. So this one.
This
Yeah.
So when you say
Yeah.
carbonatite dike, and then they say ore hosting dolomite marble, those I'm assuming are rocks without silicate in them. Yeah, you're getting the zircons. They are getting the zircons out of it. Is that right?
Yeah. I can answer that if you want to. Please continue.
Okay.
Yeah.
So my question is, so carbonatite smelting at 600 degrees. Why would we expect the zircon to record the age when closure age is so much higher?
Yeah, but I mean but
If they're inherited, and they're then going into a lower temperature melt,
yeah,
that would just stay inherited,
yeah,
right?
that could explain this old
But
population.
also could
Yeah.
be inherited, couldn't they? It's only 600.
Yeah,
degrees,
but I think
they're
I think there's good geological constraints that it isn't younger than 100 million years. And I don't know the regional geology well enough to say why they can be certain that, it can't be younger than that. There's probably other good reasons, and of course other geochronometers, but they also have, issues. If you think about, argon dating of biotite, continental systems often has excess argon, so you may be again too old.
I guess what I'm trying to ask is, so if they don't, so the clock turns on due to a thermal event. If your thermal event's not high enough, what is it actually recording?
Now, as soon as you form a zircon with uranium, the uranium will start decaying. The zircon can form at 600 degrees, it can form at 900 degrees.
So you think that they're actually crystallizing in the carbonatite, they're not inherited?
These authors interpret these as magmatic zircons,
Okay.
from the carbonatite, avoiding the question, why would a carbonatite in the first place crystallize zircon? But
Yeah.
putting that aside, then they would basically say, okay, yeah, this is a magmatic crystal, and so that's the crystallization age or the formation age of that carbonatite.
Okay.
Yeah.
I see where
Yeah.
you're going. Yep.
Have you looked at the hafnium isotopes in those 50,000, across that 50,000 years?
Yeah.
Okay, and do you see detailed changes relating to different amounts of country rock assimilation?
Let me pull that. Actually, I have that here. So you can see the isotopic composition of the carbonatite zircons, which are those red symbols, and every symbol is actually an average of multiple spots on a single grain. We didn't do too many of these carbonatite zircons, but we compared it to zircon megacrysts that sometimes found in these alkali lavas. There are similar zircon megacrysts associated with these the tertiary volcanism here in Western New South Wales, Eastern New South Wales in Australia. They're also associated with alkali volcanism. So this would be these open and these closed symbols here. And what we can see is, when the x-axis is always a fractionation index, zirconium, hafnium, and here europium star. If it was closed system fractionation, you would pretty much go, with of course an isotopic they're always the same isotope values. But the trend, if you look at the whole population, at the whole system, it actually always is a little bit, it follows an AFC trend, which suggests that there is some crustal contamination going on. So I would not say that these are 100% mantle derivatives. There is certainly a little bit of crustal contamination, but that crustal contamination probably happened very early. It already affected, the spasonites and the mafic phonolites.
But on that diagram, the most negative hafnium is always in your carbonatite.
Yeah.
So, and look at that, that's a huge spread when you go to the other volcanic systems.
Yeah, yeah.
This direction or data screening to make sure that thorium system is closed?
I mean, if you look at diffusion experiments for thorium and uranium, I always say, if to the students here, if a PhD advisor comes to you and proposes to you, you study uranium diffusion or thorium diffusion in zircon, saying no, you will not get a result under any circumstance in your PhD time. The diffusion is extremely slow, as orders of magnitude slower than lead. And even lead is, we have closure temperature of 900 or 1,000 degrees for the uranium lead system in zircon. So diffusion of uranium and thorium, it's not going to happen. And so this is why the system is a very robust chronometer. The exception is this dissolution reprecipitation, but there you really change the zircon, the chemistry and
Yeah, there is now because like you said, water and zircon is very good texture.
yeah.
And we did that because last month I was checking my previous group, they had also zircon from the prototype. They got 10 scale zircon age, so they were trying to do more long analysis from their good crystals.
Yeah, no, it's certainly a problem for uranium lead, especially because these have very often high thorium and uranium abundance. So metamicalization is a huge problem. But with regard to the uranium thorium system A, it's very young in this case, and it's also the diffusion is much slower than even lead. Okay, John.
Yeah, so if you take that 1350 age, that puts you at the same age as a number of things around the world, including, Mount Weld and the Gascoigne and Mountain Pass.
But Mount Weld, I would say, is older, right?
It is older,
Yeah.
but the Gascoigne is clearly 13,
Yeah.
50,
Yeah.
that the Mountain Pass is clearly that age.
That's true.
And
Yeah.
there's some arm waving about breaking up of Columbia, and that's
Mhm.
how there's a moment when I know that age is often difficult to say when an imagined supercontinent is breaking up. It's kind of hard to know exactly what it did. But could you comment on that and how and why that would affect, for instance, carbonatite formation at one moment?
Yeah, probably. No, I probably shouldn't comment because I know too little about it. About these old carbonatite systems. I mean, carbonatites or these alkaline interplate systems are often related to extension, and that's the case. Here we pretty much have, the Rheingraben forms as a effect of the alpine collision. We get east-west directed extension because of the north-south directed collision. And the timing works pretty well. The Rheingraben starts to rift, at about the time we have alpine collision, and that's also when the Central European volcanic province starts to form. But then there are only very few carbonatites in that system, including one is this Kaiserstuhl, which is erupting when that has already been, going on for many tens of millions of years. The rifting. And then Laacher See is, again, a very, very young system. Besides that, there's just this very general, relation between, rifting, extension, decompression, melting of small volumes in the mantle, which is favorable for forming carbonatites. I don't really want to say, too much speculative things.
It's interesting, at Laacher See, you seem to have your zircons forming episodically. Does that mean that you're not just continuously growing zircon in that system, but something needs to promote the growth and then it stops for a while, then it starts up again?
I think so, yeah. And it's maybe a little bit related to my answer to Michael. You know, maybe that process happened multiple times. We had multiple pulses. So I would subscribe to such a scenario, yeah. That it's not necessarily a continuum, but multiple pulses.
Are there any monocytes?
They are not in the cyanites. They are actually in the phenites. By monocyte, yeah.
And you,
Not yet. I would like to, yeah.
There's monocyte at Bionova.
Sorry?
There is monocyte in Bionova.
Ah, yeah, yeah. I think that's some ages, I guess, mentioned also on the monocytes. Yeah, yeah.
Okay, let's then thank Axel again. You can sign up for the dinner. The list is on the table. Going to the lemongrass side at the Melbourne building. Thank you.